take a look at the bell work here. So in this case, we are being asked to graph a cotangent function. Now we have done, we talked about cotangent before. We've only done tangent, examples of tangent together though. So I wanted to make sure that you guys saw this before the test that you all have on Wednesday. So this is, we are told that f of x is equal to cotangent of, this is 1/4 times x plus pi over 4 plus 3. We're going to go through our standard kind of litany of questions here, make our normal adjustments, although we'll see kind of how they are different to what we would typically be doing, and then we will we'll graph this thing. So we are looking for, as far as information, amplitude, what is the period, what is the phase shift, vertical shift, and midline. All right, for our amplitude, what is the amplitude of this function? None. There is no amplitude. Now, 1 would be not a bad guess, and 1 would be very consistent with every other trig function that we've done there, looking at the coefficient. But amplitude refers to like the size of the wave for our trig function here. And when we're looking at like cotangent or tangent, there isn't a wave. Like there isn't a wave in the way that we would see with like sine or cosine, or even with something like secant or cosecant, because these aren't really waves. There just isn't an amplitude. This is not a question that we would really even ask. What is the period for our cotangent function here? 4 pi. So what is the standard period for tangent and cotangent? Pi. Dividing this by that 1/4, dividing by 1/4, the same thing as multiplying by 4. Absolutely correct that this would be 4 pi. What is our phase shift here? Negative pi over 4. Very good. Vertical shift up by 3, and then the midline, y equals 3. Very good. Questions with what we see here? Okay, so then the next thing to do is to make adjustments to our y values and our x values. With tangent and cotangent, what is the only y value that we actually care about here? What is it? Yeah, it's only the mid value. So it's just what happens to 0. This is part of why we don't really concern ourselves very much with like what's going on with the amplitude, is because the amplitude doesn't like act on the values, like the significant values that we care about. If I were to multiply my tangent function by 2, then I would, or cotangent by 2, I would multiply 0 by 2 as my first step, and that would do absolutely nothing, right? That would just not change my value here. So what is the adjustment that we make to our y value here? We are adding 3 to it, and so we will see the mid value at 3. Okay. Now with tangent, what were our 3 significant x values that we were considering? Yeah, negative pi over 2, 0, and pi over 2. Those were a little bit weird compared to what we were normally working with. Why did we pick those three? What was significant about choosing negative pi over 2, 0, pi over 2? Yeah, it gives us like a clean, unbroken picture, like a clean snapshot of what we have going on here. In particular, it takes us from asymptote to asymptote. So negative pi over 2 was one asymptote, pi over 2 is another, 0 is what falls between them. We want to go consecutive asymptote to asymptote. Could we also have done pi over 2 to 3 pi over 2? Would that also take us asymptote to asymptote? Yeah, absolutely. We totally could have. You even could have done 0 to pi. Your function would just look a little bit funky. It would look broken up and strange. And so we picked these a little bit more carefully than that. But generally speaking, the goal is to go asymptote to asymptote. Now, tangent, in terms of sine and cosine, what is tangent? Sine over cosine. And so where did these asymptotes come from? Why do I see asymptotes at negative pi over 2, pi over 2, 3 pi over 2, 5 pi over 2, so on? They're not so there's something to do with what they are with sine and cosine. What do they correspond to here that's significant about sine and cosine? Pi over 2, 3 pi over 2. They are the max and mins for sine. That's certainly true. What's going on with cosine at the same time? They are the what of cosine? So what is cosine of pi over 2? 0. What's cosine of 3 pi over 2? 0. Cosine of negative pi over 2? 0. These are the zeros of my denominator. They're the zeros of cosine. Right, so that's for tangent. The reason why we're looking between negative pi over 2, pi over 2, we go asymptote to asymptote. The reason why our asymptotes are at negative pi over 2 and pi over 2 is because those are the zeros of our denominator. Our denominator in this case is cosine. For cotangent, what is our denominator now? Well, we're going to look there. We're going to look for where it's 0. But what is the denominator of cotangent? Sine is the denominator for cotangent. And so when is sine equal to 0? Yes, of course, I can look at the board and read the fact that the zeros of sine are going to be 0, pi, and 2 pi. Very good, children. Very, very good. It's up here, guys. Come on. Like, I realize it's Monday. I realize it's a dreary day out. I realize it's a math class at the very end of the day. I have been there. I have taken math classes at 5 o'clock at the end of a 7-hour day. Let's be with
Hey, yes. Can I see gold mines real quick?
Absolutely. All right. Awesome. So rather than looking between negative pi over 2 and pi over 2, what is our standard for cotangent? What two values do we go between for asymptote to asymptote? 0 to pi, and then what's going to be in the middle of those two? Pi over 2 in the middle of those two values. All right, what transformations are we making on our x's here? Before that? So first we have to divide by 1/4, but dividing by 1/4 is just the same as multiplying by 4. I get 0, I get 2 pi, I get 4 pi. And then what is my second transformation that I'm applying? Subtracting by pi over 4. I get negative pi over 4. I get 7 pi over 4, and I get 15 pi over 4. And what do these correspond to? Well, our edges here are both asymptotes, and the value in the middle is our midline value. All right. So we are mostly to the right of the x-axis, a little bit to the left. One value to care about to the left. We'll plug in, we'll go ahead and we'll do this. We'll say negative pi over 4. We'll say, no, that's a little bit far over. We'll say that this is negative pi over 4. We'll say that this here is 7 pi over 4. We'll say that this is 15 pi over 4. We've got our midline up here. Not happy with. Midline up here at y equals 3. And what do we know about our edges here? Well, they both represent vertical asymptotes. And we know that this middle point here is on the midline. Now, you can just memorize the direction that cotangent is going to be between and the direction that tangent is going to be between, and that's fine. There's nothing wrong with that. But let's try and go through it logically. Let's try and go through it conceptually. If I am between 0 and pi over 2, what quadrant am I living in? First quadrant. What do I know about cotangent in the first quadrant? Positive, we are going to be above the midline. Between pi over 2 and pi, what quadrant do I live in? Second quadrant. And what do I know about cotangent in the second quadrant? It's going to be negative, positive y, negative x. When we divide them, we'll get a negative. And so my function will be below the midline. We end up with something like this. The reason why tangent is the opposite is because between negative pi over 2 to 0, what quadrant are we in? Negative pi over 2 is a little bit of a weird one, but remember, what does the negative angle tell us to do? Fourth quadrant, right? We're rotating backwards by pi over 2, clockwise by pi over 2. And what is true about tangent in the fourth quadrant? it's negative, which is why we see from negative to positive, whereas cotangent goes from positive to negative. It's the difference of going from starting in quadrant 4, ending in quadrant 1, and starting in quadrant 1, ending in quadrant 2. Yeah, but you won't necessarily be able to get a super clear image of like what the values are for like negative pi over 4 or 15 pi over 4, things like that. Yeah, so cotangent would be flipped. Yeah, 1 over. Yep. Now, it's not quite just because all of the zeros become asymptotes, all the asymptotes become zeros. But yeah, and then it like flips upside down. Yeah. Yeah, for all of them. But you still run into the same issue of like finding out like the x values, the proper x values and stuff that it corresponds to becomes hard because you're looking with rational. Yeah. Oh, yeah, yeah, for sure. All right. Other questions here? Good question. On the study guide for the test that we have on Wednesday, there is a question, I think it's question 11, deals with graphing either cosecant or secant. I think that one was cosecant, but obviously the technique between the two, very, very interchangeable. There isn't one for tangent or cotangent, mostly because you can probably kind of tell once you attempt the number 11 that these graphing problems on Schoology are not very pleasant to write. And so I didn't do one for tangent and cotangent. That being said, that is not to say that it will not be on the test. Think of what we just did right now as an extension of the study guide. Right? We just did the fictive number 12 together. Now there is a number 12. Number 12 is basically just my telling you, hey, I'm aware that tangent and cotangent graphs aren't on the study guide, and I need you to be aware that they will show up on the test anyway. So just a heads up, even though it is not technically on the study guide, I am telling you, think of this, what we just did now, as an extension of what should be considered to be on the study guide. Complete with a recording to go over, since we are recording this. Yeah, Simran. It's supposed to be cotangent, cotangent of theta. I don't know why it shows on my end as being cotangent of theta. I don't know why it's not transferring over. It might be, did you start it this morning? It might be, that might be why. But yeah, it's supposed to be cotangent of theta. All right, we have what in theory could be a relatively short lesson. We'll see. This one is practically not all that difficult. We do have a little bit of work to put in conceptually, which is going to be the bulk of what we are doing today. It's kind of going through some of the conceptual ideas of 4.7 here. Very similar to kind of how we did Unit 3, we have worked on kind of establishing a function, and then we spent in Section 3 a very large amount of time working with the inverse function that was attached to our original function here. We're going to do the same thing. We're not going to spend nearly as much time with this as we were with like logarithms or things like that. But this is still fairly important. This is still something that I want us to be pretty familiar with kind of as we move forward here. Before we get into the inverse functions themselves, I do want to take a little bit of time to kind of hash out or readdress some of the information that we have worked at so far. So we are going to focus on what's going on with sine and cosine, and then we're going to take a look at what's going on with tangent as well. We haven't really talked about tangent all that much as a function. We'll get a little bit of time to do that today. Going to start with the domain for both. What is the domain of our sine and cosine? Are there any restrictions on like what we're allowed to plug in for our trig functions here? No. So we say that this would be negative infinity to infinity for sine and cosine. But I want to do more than just state that we can plug in any number. That's totally fine. But very similarly to kind of what we did with the exponential functions, and then ultimately what we did with logarithms, I want to talk about what that number actually means. Like, what does this number in fact represent? What are the objects that we are plugging into our function? What does this mean? What does it mean to take sine of pi over 3? What does that input represent? What do the inputs to sine and cosine and tangent and all of our trig functions, what do these inputs represent? So that is technically true. That is literally true. I mean in a more conceptual level. What are the objects that we are plugging into our function? What is pi over 3? What is 11 pi over 6? What are these all various examples of? What are they? Those aren't the inputs. So the inputs aren't coordinates. We're going to put a pin in that idea about how they relate to coordinates here in a second. They are radians, which are an example of an angle. These are angles, right? We could plug in 30 degrees, right? We could absolutely ask what is like sine of 30 degrees, or we could ask what is sine of pi over 3. Ultimately, this function is one that plugs in, takes in some kind of angle measure. Now, this is also true of tangent. Tangent, though, runs into a slight issue, which is that I can't just go plugging in every single angle that I want willy-nilly. In fact, there is a restriction on what I am allowed to plug in that corresponds to when cosine is 0, right? I get asymptotes around these values that I am not allowed to actually plug in. And so we might say something along the lines, there isn't a way to do this with our interval notation because there are an infinite number of discontinuities that we would need to kind of capture here. But we might say that for tangent, the domain is going to be all of the values of x where x is not written in the form of k times pi over 2, where k is an integer. So this is just saying it's not 3 pi over 2. It's not, I guess technically where k is an, we'll say where k is odd. There is a better way to communicate that, but we're fine with just saying where k is odd. Because like we're fine with like 4 pi over 2. That's just 2 pi. We can plug 2 pi in and that's fine. But things like 5 pi over 2, things like 7 pi over 2, negative 104, or not 104, 103 pi over 2. All of those would be zeros of cosine, and those are an issue for us because we're dividing by 0 for tangent. But regardless, they still represent angles. Now, to Haddon's point here, well, first of all, what is the range for our sine and cosine? -1 to 1. And what do these values represent? So for instance, when I tell you that sine of pi over 6, well, what is sine of pi over 6? Not radical 3 over 2, it's the other one. It is 1/2, 1 over 2. What does that mean? Where does that 1/2 come from? We know that the pi over 6 is some kind of angle. Where's the connection here? Yeah, this is the y coordinate where? On the unit circle. Okay, so our input is some kind of theta, some kind of angle. Our output is coordinate information. Whether it's the y coordinate, whether it's the x coordinate, or in the case of tangent, some bizarro combination of the two. Right? So this is plugging in an angle, and we are outputting coordinate info from the unit circle. This was our way, these functions were our way of tying together the angle information from the unit circle and transforming it into coordinate information. How do I take the fact that I have rotated by pi over 6 and use that to determine my height, or use that to determine my x distance, sine, cosine? Are functions that do that. Now with tangent, the range still represents coordinate information. But in this case, that coordinate information is a little bit obscured. It's not just the x value or just the y value, it's that y over x ratio. Looking at something like tangent or something like cotangent, is there a minimum y value or a maximum y value? No, the range for tangent is just all real numbers. Tangent's a little bit weird. Okay. So this is what we've been working with up until now, with the addition now of tangent, a little bit new. But sine and cosine, hopefully all looking pretty similar to what we've seen up until this point. Now we want to find the inverse function for sine and cosine. What does it mean to find the inverse function? Thinking back to what we did in Unit 3, thinking back to what we did in Unit 1, how do I find the inverse function? We swap the x's and the y's. Okay. So our sine inverse of x, which you will often see written, and how I am going to often refer to it, this is also written as arc sine of x, but notably, this is the inverse function of x. It's what we get when we swap the x and the y values. Very good. So what is our new domain going to be? It's going to be from -1 to 1. And what is it going to represent? Yeah, it's the coordinate information. And it's going to be outputting to a range, not to R, but to a range that represents what? Something about the angle. Okay. So sine, cosine, the standard functions, we're plugging in an angle and it's spitting out the x coordinate or y coordinate, depending on which machine we're using, which function that we're using. Inverse sine and inverse cosine, we are plugging in an x coordinate or we are plugging in a y coordinate, depending on which machine we're using, and it's spitting out the angle that corresponds with that particular x or y value. So doing kind of the opposite. It's the inverse. It's doing the opposite of what we do. We swap what the inputs are. We swap what the outputs are. Sumaran, did you have a question? Negative 1 to 1. So we're swapping our x and our y values. We're swapping the domain and the range. So because the range was negative 1 to 1, the domain is now going to, for our inverse, is now going to be negative 1 to 1. Now, that would normally mean that the range of our inverse sine would be what? Negative infinity to positive. It should match the domain from our other function. We are going to see if that holds up here momentarily. The short answer is it doesn't hold up actually well at all. Yeah, so we would say if we wanted to do cosine inverse of x, or otherwise denoted as arc cosine of x, this domain would also be negative 1 to 1, which also is coordinate information. And then for tan inverse, otherwise known as arc tangent, what is this domain going to be? All real numbers, negative infinity to infinity. We can plug in anything we want. Where? So for inverse sine, we are plugging in a y value. It's going to spit out an angle. For inverse cosine, we are plugging in an x value. It's going to spit out an angle. Inverse tangent's a little bit weird. We're going to be like plugging in a ratio of y over x, and then it's going to tell us the angle that would give us that ratio of y over x. So let's try example 1. We're going to realize, hopefully, the issue that we currently have. We'll assume that the range for now is negative infinity to infinity. Don't actually write that because it's not. We're going to rectify that assumption after we take a look at example 1a here. Okay, so we are looking at arc sine of negative 1/2. So translate this statement to me. What does it mean for us to be looking at arc sine of negative 1/2? What piece of information have we been given here? What does negative 1/2 represent? So it's the x values, the input of our arc sine function. But it's the y value of, not of our sine, but of the, I mean, actually, yes, of our sine as well. But it's a y value where? On the unit circle. And what are we being asked to find? If I give you a y value on the unit circle, I'm asking you to find the associated theta, the radians that go alongside. Absolutely. Okay. So negative 1/2. Let's start with the 1/2 bit. 1/2 for the y value tells us what is going to be true about the reference angle. What is the quadrant 1 angle that gives me that value of negative of 1/2 for y? 30 degrees or in radians? Pi over 6? Okay, so that's like the reference angle. That's like the quadrant 1 angle that we'll use. Now, where are we going to find negative y? Quadrant 3 and 4. So what would the example be for our pi over 6 angle in quadrant 3? Seven pi over 6 and 11 pi over 6. Not and, actually. This would be or 11 pi over 6. And we run into a problem. First of all, are these the only two angles that are possible that would give us this y value? No. In fact, there are an infinite number of angles that are quadrant 3 and quadrant 4 angles that would give me this y value of negative 1/2. They would all be coterminal with 7 pi over 6 and 11 pi over 6. You could add or subtract 2 pi as many times as you like to either of these angles. You'll get a set that is an infinite number of quadrant 3 angles, an infinite number of quadrant 4 angles. Cool. Why is this a problem? What does this ruin as far as us wanting arc sine to be an inverse function? It doesn't have a clear output. This is an x value that is being mapped to more than one y value. To be especially problematic, it is being mapped to an infinite number of different y values. There are an infinite number of possible y values that we could land on. Is this a function as it is defined right now? No. Okay, so it's not a function yet. We ran into the same issue when we were thinking about the inverse function of x squared. Right, so thinking back to that, inverse function of x squared, we want to plug in a number that has been squared, and it will tell us what the original number was. If I plugged in 4 into that inverse function, the problem that we ran into was that it could either have been 2 that I squared or negative 2 that I squared. I could have either taken the sine of 7 pi over 6 to get to negative 1/2, or I could have taken the sine of 11 pi over 6, or I could have taken the sine of 23 pi over 6, or 19 pi over 6, or any of the various coterminal angles that exist for these particular things. What did I do before when I ran into that issue? So when we had the issue of it's either negative 2 or 2, it's either negative 3 or 3 when I plug in 9, it's either negative 4 or 4 when I plug in 16. What did I do to fix that problem? Anyone remember? This is back in Unit 1. It wasn't exactly mathematical. Well, we can try them both. They both work. So they both work fine. There's nothing mathematically wrong with 2 or negative 2 as solutions. It's just for defining our function, we need to pick a lane. And so what did we do? Well, we picked a lane. We said either I only want positive answers as my output. So I either want from 0 to infinity, or I only want negative answers as my output. And I just chose one of those two definitions. Like, it's great that both of them work mathematically, that there's nothing wrong. And we just said, okay, I recognize that both of these work, and we're just going to arbitrarily say, I only want positives. Or we arbitrarily say, I only want negatives. We're going to do the exact same thing here. We are going to throw away, essentially, an infinite number of points until we are only left with one angle per y value. Okay, so let's think about our unit circle here. Okay, so we have our unit circle. We'll divide it into the quadrants, like so. And I want to think about a section of my unit circle where I see every single y value and I see it exactly once. We don't want to have any repeated y values along my unit circle. What could I use to make sure that I have every single, what pieces of my unit circle could I combine to make it so that I see every single y value exactly once? Give me some combinations. So the problem is if I'm using 1 and 2, I'll get positive y values from both quadrant 1 and quadrant 2. Okay, so I could use either 1 and 4, or I could use 2 and 3. I actually really like these two combinations specifically because they're connected. Now, is there anything wrong with, say, using quadrant 1 to get my positive values and using quadrant 3 to get my negative y values? No, there's nothing mathematically wrong with it. It's just a little awkward because those are like on opposite sides of the circle. Likewise, we certainly could use quadrant 2 to get our positive y's and quadrant 4 to get our negative y's. It's just what we describe as a disjoint set. So we have to pick a lane. Do we want to use either quadrant 2 and 3, or do we want to use quadrant 1 and 4? There is nothing wrong with using 2 and 3, but convention, which is dictated by people who are long dead, says that we are instead going to use quadrants 1 and 4. Right? So quadrant 1 is going to tell us what's going on. We're going to use angles from quadrant 1 for positive y values. We're going to use angles from quadrant 4 for negative y values. Now I could use like 11 pi over 6, kind of like we see here, this 11 pi over 6. The problem then, though, is that, again, it's disjoint. If we think about starting at 0 and rotating around my circle counterclockwise, quadrant 1 and quadrant 4 don't really connect. You have to pass through quadrant 1. You then have to pass through 2 and 3 before you make it to 4. As it stands, they're actually pretty far apart on the circle. The solution that we have is, rather than starting at 0, we're going to start in quadrant 4. We're going to start at negative pi over 2. And we're going to rotate counterclockwise, rotate normally, until we reach pi over 2, and that will give us all of quadrant 4, all of quadrant 1. So our quadrant 4 angles, which before were like 11 pi over 6, 5 pi over 3, 7 pi over 4, all of those, they are now just going to look a little bit different. It's going to be like, instead of 11 pi over 6, I'll use like negative pi over 6. Instead of 5 pi over 3, we'll use negative pi over 3. Instead of 7 pi over 4, we'll use negative pi over 4. All right. So theta is from here. It's like negative pi over 3, negative pi over 4, negative pi over 6, and theta's from here. This would be like our normal ones of like pi over 3, pi over 4, pi over 6. So the range for sine, the angles that we can possibly see as outputs here, are just from negative pi over 2 to pi over 2. This is quadrant 4 through quadrant 1. Tangent is the same. Well, it's mostly the same. The only difference with tangent is that we can't actually plug, or we're never going to get negative pi over 2 or pi over 2, because you'd have to like plug in infinity and negative infinity. It's not going to happen. So the range is going to be very similar. We're going to use quadrant 1 and quadrant 4. We just aren't ever going to have the endpoints here. So it's going to be pretty much the same, just not including negative pi over 2 and pi over 2 because tangent doesn't include those as part of its domain. They're outside the domain of tangent. Could we use quadrants 1 and 4 as our range for the x values? Does that give us every single possible x value exactly once? Exactly once. So the problem is it gives us every single positive x value twice. Right? If we use quadrant 1 and quadrant 4, x is positive in both of those, not going to be good for us. We are looking for a piece of our unit circle, preferably a connected piece, although again, that's just a rule that people who are long dead made up. We are looking for a piece that is connected, where we can find in half of that piece positive x values, in the other half of that piece positive y values. What would be good examples of that? Quadrants 1 and 2 is actually exactly what we are going to use here. This will be what we use for cosine. Now, is there anything wrong with using 3 and 4? Mathematically, no, there's nothing wrong with that. But we use 1 and 2 just by convention. The range here is going to be from 0 to pi. And if we do this, there is no ambiguity. We know exactly the y value or the x value that goes alongside a particular angle. Or we actually we know the angle, the exact angle that goes with a particular x value or a particular y value. So for arc sine of -1/2, we said pi over 6 is our reference angle. We know that sine is only going to spit out angles from quadrant 1 or quadrant 4. If we're looking at -1/2, which quadrant is this going to come from? 1 or 4? It's going to come from quadrant 4. Normally that would be 11 pi over 6. But 11 pi over 6 is not the connected quadrant 4. This would be that theta is equal to negative pi over 6, rather than that 11 pi over 6. Arc cosine of -1/2. Well, first of all, what is the reference angle that corresponds to the x value of 1/2? Yeah, which would be the same as negative pi over 6. Yep. And notice that it gave you -30 rather than like 330, which is exactly why. But like that's exactly why. Yeah. Yeah. What is the angle that corresponds with an x value of 1/2? Which in radians is pi over 3. You're good. In this case, we are negative. So what quadrant is that going to be for inverse cosine? Where do we pull our negative values from? Second quadrant. What is the second quadrant angle that goes with pi over 3? 2 pi over 3. All right, one last one. Tangent and arc and tangent just is a little bit tricky because again, it's not like the x values, it's the ratio of the x values. So in particular, think of like √3 as being like √3 over 2 over 1/2, which is such an awkward, cumbersome way to kind of process it. But this helps us recognize what's going on. Our y value here is root 3 over 2. Our x value here is 1/2. What is that theta? That's going to correspond to a y value of root 3 over 2 and an x value of 1/2. Uh, 5 pi over 3, because quadrant 4, except instead of 5 pi over 3, how are we going to write it? Negative pi over 3. So correct quadrant, correct angle, but we want to write the negative pi over 3 version rather than the 5 pi over 3 version. Not that 5 pi over 3, not that that's like not correct, like sine of 5 pi over 3 or tangent of 5 pi over 3 is negative root 3. There's nothing wrong with it. We just can't have it be like both. And so we picked a lane. We said, well, we'll just do negative pi over 3 instead, which is like our arbitrary, we just made this decision and we're just going to roll with it. Smiley face. One thing that I want to harp on very, very quickly, and then we'll be done. And then you guys have the rest of this time to work on either the exit ticket that we always do before review days, which is posted to Schoology, and the study guide, which hopefully shouldn't take too long. But before we do that, one thing that I want to note, the thing that is unpleasant about the notation here, and the reason why you see, for example, why I am exclusively using like arcsine, arc cosine, arctangent, whereas like if you look on a calculator, the inverse trig functions are all like sine -1, cosine -1, tangent -1. The reason I refer to it the other way is because I don't want you to get confused with the idea that we are raising this to the power of -1, right? Raising to the power of -1 would be like taking the reciprocal, and cosecant and inverse sine are not related at all, right? Cosecant is taking our y value and flipping it upside down, and inverse sine is not spitting out a y value, it's spitting out an angle that goes alongside a y value. So the notation here can get kind of confusing when you use that like to the -1 to make matters especially fun. That to the -1 that you see that is representing that it's an inverse function is actually where the power is supposed to go for our trig functions. Like if you were to write that you want to square sine of x, you would write it as sine squared of x. If you wanted to write that you were raising sine of x to the -1, you would write it as if it's this inverse function, which is awful and sucks. And so just to be completely unambiguous, I like to write it as arc sine, arc cosine, arc tan, rather than sine inverse, cosine inverse, tan inverse. Not that there's a difference between the two, just because script-wise, it makes it very, very clear that we are not working with cosecant or secant or cotangent. All right, that's all I got for you. Done with Unit 4, done with the first, I guess, like third of what we're going to be doing with trig. Because again, Unit 5 and 6, still going to be trig. Oh yeah, oh yeah. This is the preliminary. Well, yeah. Unit 6 is easier. Unit 7 is a little harder. Unit 6 is easier. All right. So there's the study guide. Make sure by the end of today that you tell me what you would like to look at tomorrow for in that October 30th exit ticket that's on Schoology. And beyond that, we got a little over 20 minutes left. You guys have the rest of this time to work on the study guide. Yeah, quadrant 3 doesn't get used. You'll never see an inverse trig function output a quadrant 3 angle. Quadrant 2 is just normal. So it's like 2 pi over 3, 3 pi over 4, and 5 pi over 6. Yeah. Yeah, the one that I want to note is that quadrant 4 is different than the quadrant 4 angles that we have used so far. It's just the negative versions of the quadrant 1 angles. That's really the only change that we're going to be using. Yeah, absolutely. It's for yeah. 2 pi over 3 is the solution for not for A. For A, the solution was negative pi over 6. Yeah. So wait, what's the question? So why did we have to adjust these? Because that's just quadrant 2. So the reason, the answer to your question, why we had to adjust these, and I'll show you why we didn't have to. If we think about this normally, starting at 0 and rotating around our unit circle, are quadrant 1 and quadrant 4 connected in this way? But we want them to be. We want to have like a single unified, like we just run through these values. There are no breaks, there are no skips. So the way we do that is rather than starting at 0 and rotating forward, we instead rotate backwards a little bit, rotate back to negative pi over 2, and then we go from negative pi over 2, rotate from 0 up to pi over 2. That's why we do this. Do we have to make such adjustment to start at 0 and end at quadrant 2? You don't have to adjust anything because it's already constructed. So that's why we adjust quadrant 4 is to make it mesh. And we don't have to do that because quadrant 1 and quadrant 2 is less than each other. Good question. Yes. So what does it mean for this function? Yeah, so when you plug in negative x, it'll start with the negative version of the function. So you're going to use the odd, even properties of sine and cosine to figure out which of those. So when you plug in negative x, which ones are going to flip, which ones are going to stay the same, and are there any relatives? Although this makes no sense. But that's what you need. For 20 minutes. You can start it and then finish it. Yeah, for sure. It's interesting to watch.
There's no trust. I don't let it be.